Okay, and see how it works. So, let's talk about, Timothy's late. It's really settled into a regular semester now. So let's start talking about, I want to start talking about hashing and just remind you all of what we were talking about last time. That under the primary hashing method, we have an array of linked lists, and you use a hashing key, and the hashing key tells you which index in the array you're in, and with a linked list array, you keep on building off like so. So you keep on inserting elements when there's a collision. Under, when you start talking about the open addressing method, there's an alternative to this, where rather than inserting the collision element at the specific index, you insert it, so A, B, C, you keep on inserting them in order. And so you eventually wrap around once you get to the end, and you keep on inserting them. The big problem with this approach is that it creates clusters of elements where there's lots of collisions, and those clusters compound, because now everything that would have collided there now collides with elements that are there, and there, and there, and so on. And so you create this really long cluster, which is bad not only because it increases the probability that things will actually hit each other, but it also increases the length of time. Because now the time complexity to access something is the number of possible collisions you can have in a row. So the solution for this is to use what's called, use linear probing. And so here we see an example of linear probing that you all can step through on the slides afterwards. And again, my awesome animations. We have double hashing. Double hashing, rather than just automatically inserting in the next element, what you do is you use two hashing methods. The first, when there's no collisions, it behaves as normal, so you use your normal hashing method based off of your key, that calculates where you should go into the array, you're done. What happens the next one is you use an alternative hashing method. And again, you can make these hashing methods however you like. The system is not picky about how you make them. Now, in the upper level version of the class, we talk about how to make those hashing keys so that you actually get a really good distribution. We do what's called perfect hashing. Not going to cover that in this class. But hashing 2 is interesting because what happens with this is that it kicks in differently based on the number of times that you have collided. So if you never collide, and I represents the number of collisions you tried to do. So you collide 0 times. Hashing 2 has no impact. You collide once. So suppose you were to try and find, you inserted A, and A was supposed to go here. Now you want to insert B. And whatever hashing method you have causes a collision at B. You now figure out what is B's hashing method. So you run B through hashing method 2. You take that value and multiply it by 1. Now, so that inserts B somewhere in here. Now suppose you collide A, B, and now you have another collision. So let's say you want to insert C, and it would have hashed to A. Oh, something messed up, and now tries to hash to B. Oh, there's another collision. What you would do in that case is you would do hashing 1, hashing 2, 2 times the hashing method. And again, you modulo the whole thing by 5. Modulo, for those who haven't taken computer science yet, is calculate the remainder. So you calculate the remainder of the whole thing by the size of your array, so that way you insert it in the proper element.
So if there's no collisions, it doesn't do the second method?
Right. You only calculate the second method if there's a single collision. And the advantage of doing this is that with this double hashing approach, it dramatically reduces the likelihood that we will have a chain of collisions. Under linear probing, you are exactly guaranteed to have a chain of collisions. Like linear, that is what linear probing does. Double hashing is not likely to have that. It's still possible, but you're not expected to have that.
Can this one fill up too?
It can absolutely fill up. And so it doesn't solve the fundamental problem that you can still fill up your array. So in order for this to work, you still have to have your hash table, your array needs to be sufficiently large.
So doesn't this just cause collisions in a different order?
It does. And so when we're talking, and this is one of the subtleties of this, is that when we're talking about the worst case scenario, this does no better than linear probing. Because in the worst case, this can screw you just as bad as linear probing can screw you. But in the expected case, this is less likely to happen. Because linear probing will still have this, will always have line of collisions wherever there is one. And so that's just a feature of linear probing. This one can still have that, but the chances of you having, hashing method was here, hashing 2 on the second collision was here, 3, 4, the chances of that happening are so much lower that it ends up producing a much better result in practice. And so generally you do not see hashing linear probing done in practice because its real world performance is so poor that double hashing is so much easier to do. All you have to do is come up with 2 different hashing methods. And there's a range of perfect hashing methods you can go and look, basically literally open up the data structures and algorithms textbook and get them out of there. And so you can get 2 different hashing methods and then you're done.
I is the number of collisions?
I is the number of collisions. Does this make sense to y'all?
What's D in that equation?
D, that's the specific location where you're supposed to insert. That's where you should insert the destination. So the destination off of the key for the ith collision. Cool. Any questions? Riley, you seem contemplative. Okay.
I was just figuring out what K was.
K was the key. Yeah. So K is the key, I is the number of collisions. So hashing is great. It has some severe limitations though. It is terrible at order data structures. How do you find the largest element? If I wanted to say, give me the largest key in a hash table, how would you do it? No, that's not going to work because things are now basically inserted randomly into the list. You have to go through, and it's worse than that. It's worse than that because in an array, I could go through every element and find the last one, right? However, in a hash table, I have no idea which elements have been filled and which ones haven't. If I've done my hash table correctly, I've created my array so much larger than my data set that I would have to go through every space that's been allocated and those not yet allocated to find out what the largest element is. Basically like, nothing here, nothing here, nothing here, nothing here, nothing here. Ugh. There's no realistic way to keep track of what is the largest element in a hash table. They basically cannot do it. There's actually no way to keep track of what are all the elements in a hash table. You have to use another data structure to keep track of everything that's in there if you want to get what is the list of everything that is in this array. There's no good way to do it. Yeah, but again, that only works if elements are never removed. If you remove an element, then you're completely shit out of luck. Yeah. You also have to allocate more space than you intend to use in order for these to perform well. They work because we sacrifice upfront a whole bunch of space. There's also no guaranteed performance. I guess there is, it's terrible. In the worst case, you go through every element in the array. If you're using an open addressing approach. If you're using the linked list approach, then you have to go through the maximum number of possible collisions times the number of spaces, and that's your time complexity. That's what I like to call massive. Okay, so with all of those questions, how could we solve that? That seems like a good topic for exactly the next lecture. Oh, how convenient, priority queues and trees. So, how many people have heard the term trees, priority queues, and what have you? So, I want to separate two different categories of things for data structures right now. The main thing that this is going to be important as we go on is that there are essentially interfaces and implementations for each data structures. And these are parallel to what you all have done in Java, where interfaces define all of the methods that can be used, and implementations are the exact way in which we use them. The reason why I want to separate this out is because oftentimes the implementations for a particular interface are so obvious, and so once you've solved it that way, you're like, why would I solve it any other way? That we give them the same name. But it's important to keep them separated because it is possible to have data structures that have different implementations on the back end, but do exactly the same thing. And so let's talk about arrays. So an array for an interface has the methods get I, which gets the ith element, set I, which sets the ith element to a particular value, and size, which gets the size of an array. I can implement this as a contiguous memory allocation. This is exactly called an array because it's exactly how you would want to implement it. But I don't need to implement it using this. I could also use a linked list. I could also use a hash table. Would I ever want to implement a hash table using this? In no way now. Would I want to use a linked list? That's actually not a bad option for this. Linked list has some different pros and cons of it. Because getting I, setting I, if you're inserting an element, if you wanted to add an insert in here, it wouldn't be so bad. But it's still the best way if you just have to get, set, and get the size. Array is what you want to do. So it makes sense. How would I implement the interface of an array? I would use this other thing called an array. Do you have a question or just hand dancing? So let's talk about a stack. So aside from the interesting sort of homework assignment I gave you today, how many people have heard what a stack is? I guess we talked about it a lot in core 2. Did you all, those of you who were in Higgs's 121 class, did you all talk about what a stack was?
Yeah.
Things specifically.
All right. So let's talk about what?
That was foreseen last time.
Yeah, he'll change up sometimes if he covers it or not. A stack is a very interesting data structure. Now, you all had some exposure to it because I forced it upon you in the last lab. At least I gave you the name, but I didn't tell you how it works. So let's talk briefly about how the stack data structure works. The general idea is it's what's called a first in, last out interface. The idea is that if I give you a whole bunch of values, so let's do some names. So just throw some names at me. Bob? Okay, Bob. And then,
Jim.
what?
Jim.
Jim?
Heisenberg.
H. I'm a little uncertain about Heisenberg, though, I have to say. Physics joke. Look at it. Wait, oh, it changed something else. See. I'm sorry. We'll still call him H. Okay. What are their silly names? What? Bender? Okay. Okay. So let's talk about the different ways. So the way a stack is going to work is we're going to do what's called pushing elements on and then popping them off. We push an element onto a stack. So we say we can push an element onto a stack and it stores it. When we push the next element onto a stack, it stores it as well. The thing is that now this first element is essentially inaccessible. We can only push elements on the top, and then we can only remove them from the top. So we have Bob, Jim, then H, then Bender. And so when we push Bob, it goes in the stack. Push Jim, goes in the stack. Push H, goes in the stack. Push Bender, goes in the stack. We now have a top operation, which can return to us what is the last element that was pushed onto the stack. So if I were to call top on this, what would be Bender. So top would return Bender. There's also pop, and pop would return Bender and then remove it from the stack. Stack data structures are unbelievably important. The reason why stack data structures are so important is because very often we need to keep track of our past. When we talk about calling a function, whenever you call a function, those of you who are in courts, you're like, not this again. The way you call a function is you actually push all of the data onto the stack. And so you have to push all of the old variables onto the stack, but when you get to the new function, you can access them with a clean seg. We saw it in the interesting sort algorithm, where we were using it to keep track of where we were in the array. We didn't need to access the whole thing, we only needed to access what was the last subrange we cared about. And so that way, when we had our interesting sort, and we split it up into two separate subranges, the stack could keep track of, oh, the first one was between 3 and 150, and then 151 to 1138. And so we kept track of, on our stack, 3, 150, 151, 1138. The stack kept track of those two elements. We could work on there. And then eventually, once we had correctly finished that range, we would then go back to 3 and 150. And we could start working on that. But we'd work on them in the reverse order that we pushed them onto there. Any questions about that? So we saw one way to implement it already, using an array. Where we use an array that's allocated of the maximum size that we can have, and we have a top value that keeps track of where is the top value in here. When we want to push an element onto it, we increase the top pointer by 1, and we put the value in that new index of the array. When we want to pop, we get the value that's at the current top index, and then subtract 1 from the top counter. If we want to get the top, we just return the value that's the current top. If we want to do isEmpty, we return true if the top is equal to -1, and we return false otherwise. Does that make the interesting sort algorithm make a little more sense? For those of you who stepped through it, that's what was going on with the high and low operation on there. Deshaun, did you?
So in the lab, we should actually use a stack object instead of an array, calling the stack.
You're talking for the merge, or for the when you're doing the interesting sort. You could actually re-implement it with a stack. I believe Java has stacks built into it. So yeah, you could implement that with a stack as opposed to an array. And that'd actually be a better implementation because it can go as high as you want it to. The way that array approach only works if you know the maximum number of elements that are going to be in there. And you basically throw away 6 spaces for another one. The other approach is to use a linked list. And you use a linked list sort of backwards, where you keep on pointing back to the previous element. So if you talk about a linked list data structure, you start off, you have nothing. We now make a new element, Bob. Bob has a pointer which points to nothing to show that that's the end of it, and it has Bob in here. We now make another Jim, and Jim points to the memory location of Bob. You now make another H. H points to Jim's memory location. And then Bender points to H's memory location. What's the advantage of doing it this way as opposed to an array?
It's only as big as
Right. What's the disadvantage of doing it this way?
More overhead.
Yeah, there's going to be more overhead per slice. So if you know how big it's going to be and you know it's going to hover around that size, this approach doesn't work as well. If you know how big it's going to be, but that being said, generally with stacks you don't know how big they're going to be, and so this is typically the preferred approach for it, is using a linked list to implement it. And you always keep track of which is your top element in there. In fact, this is exactly a linked list. The only difference between it is rather than that being next, it's basically just last. It's a linked list in reverse. Any questions about that? Okay, let's talk about queues. Queues are the opposite of stacks. The way queues work is when you push something onto the queue, you push it to the front of the queue. When you pop something off, you remove the first element on there. So whereas you push these on, Bob, Jim, H, Bender, and you pop, which one gets removed? So if you with stacks, you push Bob, you push Jim, you push H, you push Bender. Bender was the last one pushed on, so when you pop, Bender's the one to get removed. With a queue, it's the opposite. You push Bob, Jim, H, Bender, the first one that gets removed is Bob. How many people here are British? How many people have been to Britain? You know how they call lines queues? That's what this is from. This was invented by a British computer scientist. So he called them queues because they're lines. And that's exactly what they are. You get removed in the order you're put in there. It makes it very weird when you talk to British people. They talk about, oh, I'm just waiting in queue. And you're like, you're waiting in a data structure? It becomes very confusing. So what are some ways I could implement this?
Networks?
What?
Or are you asking?
No, wait, not where would I use it, but how could I implement it?
You can use it with a printer, because like the
Not where can it be used, but how would I actually build it? What? So there are places, it's commonly used when you talk about network packing. It's also, you talk about printer queues, whenever you're sending files to the printer. It creates a queue data structure and stores it there. These stacks and queues represent two of the most commonly used data structures. So they're extremely useful. But how would I actually build this?
Could use an array.
Yeah, I could use an array again. And now I'd have to keep track of the difference between before, where they only had to keep track of a top and a top. Now I have to keep track of a top and a bottom. It's actually a little bit trickier to keep track of than a stack, because so we have a queue. So I'll put Bob, and then I'm sure I'm embarrassing names, Jim, H, Bender. So I have to keep track of bottom to where's the last what's the last element in there, and then a top, which represents the first element in there. So if I want to pop something off of it, what do I do?
Increment top, return.
Yeah, you increment top and return the value of Bob. Now what happens when I want to push something onto it? Top doesn't change actually. Now it's bottom. I increment bottom and put Aaron in there. What's going to happen eventually? It's going to circle around. And so you have to make sure here, because now notice we have 4 elements here, we've shifted 1 element to the right. And so that's going to happen, eventually going to have an overrun, where the bottom's going to come over here. And now you're going to have to start inserting elements there. And you have to keep track of those two as you go along. This is sometimes called a circular buffer, because you're always using the same set of space, you're just circling through it. Now, you often find queues implemented this way, as a circular buffer. Does anyone have an idea why you would want to implement it this way?
Save space.
You save space as a known quantity. Where do you think you might use a circular buffer like this? Buffer.
We did it.
Yeah. Who remembers who? I know we talked about it last
I
semester.
mean, literally for like video streaming.
Yeah, for video streaming. For when buffering, it's talking about exactly this. And the reason why is because when you're watching a video, you want to download a set number of frames to keep yourself going. You don't want to keep more than, say, 10 seconds of frames on your computer. So when buffering, what's happening there is literally filling up a sufficient number of spaces so that it can have a continued flow through there. And you don't want to allocate too much because you don't want to download 2 gigabytes of memory on your computer at one time. So just make sure it has enough that it can play and cycle through it. And when the video times out and starts buffering again, what's happened there is the top has actually reached the bottom, and they've gotten too close to each other, or they've actually become the same value. And then when they become the same value, it's like, I got no footage, I can't do anything. And so then it has to start buffering again. Good job remembering from last semester. The next one is called a priority queue. Priority queues are generalizations of stacks and queues. Here we insert elements by their keys, and what we have is we insert elements. We have insert an element with a particular key. We can extract the maximum element with a key. We can just get the max with a key, and we can determine if it's empty. This is a generalization of stacks and queues, because what you can do here, if you want to, you can, when you insert the element with the particular key, if you're inserting with a stack and you always want to make sure that you're inserting the maximal element, you insert elements with a key that start at 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and you also just sort of keep track of what is the maximal key that you're keeping track of. Queues, you just flip the order. So you start off inserting the maximal element to begin with, and then keep on decreasing it as you insert other elements. So you can use a priority queue interface to implement either a stack or a queue. You don't generally do that because stacks and queues are so widely used that they're worth having their own special implementation for. And that implementation is usually dependent on the particular scenario you want to use it for. Now a real interesting question becomes, how do we implement this? So I'll throw out some options. Hash, array, linked list. Those are what we have so far. What's the time complexity of insert and extract max for each of them? Okay, let's do hashing first. I probably put it first for a reason. Okay, what's the time complexity for insert? Assume best case scenario. I know we don't do that, but let's just assume expected case.
Constant.
It's constant. Okay, that's looking pretty awesome. Extract max.
Worst
Infinity.
possible time.
Basically the worst you will ever do. Yeah, because we mentioned earlier, the time complexity of all those which have been inserted and those which have not yet been inserted. It's just a small amount of time. So, yeah, we don't so much want that. How about arrays? For insert, it's actually not quite as constant. So it depends. We can make insert or extract max constant.
Yeah.
So if we have insert being constant, what are we doing?
You're just putting it at
You put it at the beginning or the end. You basically pick one, insert it there, deal with it. Then how does extract max work? You have to search through the whole thing. Now that's get max. What does extract max have to do in addition to that?
Remove it and then shuffle it.
Shift everything back down. On top of that, it's going to be, so it will be order n for extracting just the max, inserting. We run into a bigger problem that comes up here, which is that's actually a pretty terrible, like even though the order n time complexity is not so bad in and of itself, in practice it's going to be terrible because you're always hitting n and then reshuffling your entire array. But you actually hit an even bigger issue here with arrays. which is that they have a limited space size. So you have to know in advance how big your data structure is going to be. If you do, then it's actually not terrible, but oftentimes with priority queues, you don't know how many things you're going to want to store. And so then it's becoming a real deal breaker. What?
When we made it for,
We made priority queue and it's-
what did we use for array?
We made it with an array.
Array list?
They did.
No, we made it with an array.
It was array list.
A tree, didn't it?
I don't know, we made them in 120.
Oh,
We made priority
well,
queue.
I'll get to that in a second. I'll get to it in a second about how to actually start doing it. You can do it with an array, but again, it kind of sucks.
Those are spring pretty low.
It's great. It was super fun. There are prospective students here. It was not sarcastic. It was great. It was like so much fun. I'd rather be there than Mexico.
Oh, yeah.
So wait, what, like C for extract max for array?
It's gonna for extract max for an A is gonna be order n, because you have to find order n to find it, and then order n to reshuffle everything that goes on in there. Then we have linked list. Linked list has a similar thing, except in practice, linked list is going to be it still has the same time complexity. Insert can still be constant time, because you can just keep on inserting at the head or the tail, and that's fine. But we do run into an order n issue when we talk about extracting max. But what's the big difference between extracting max and extracting max from array and linked list?
You know where the max is?
And not if you're just inserting at the tail end. Why would a linked list be better suited for this than an array? For extract max,
You don't have to shuffle.
you don't have to reshuffle them around. So you can just pop an element out of there and then glue that things back up. So none of these are particularly appealing. So now we get to trees, which is what I'm sure. Trees are a vast improvement on linked list. So whereas linked list elements would always point to the next element in their list, trees point to two elements. Trees will point to a subtree, which is everything which is smaller than the current element, to the left, and everything which is to the right is everything which is larger than it. If you have things that are equal to, you basically just need to make a decision: are those always going to be on the left tree or the right tree? And just deal with that. So let's talk about a couple terms really quick. It's called the root. Why do you think it's called the root? The beginning, even though, trees are always drawn from top to bottom like this. It's an upside down tree. I guess it's like from Castle in the Sky, if it's upside down. Wow, that's a bad reference to an obscure anime film. Quality exercise. What?
Just another day.
Pretty much. So the root is, the tree is upside down, so that represents the root of the tree. We have a parent and child, and so this can be any two nodes. The parent is the one that is closer to the root, and the child is the one that's farther from it. We have siblings, if they share the same parent. We have internal nodes, which are everything which is not the bottom row. So if there's a node beneath you, you are considered to be internal. Leaf nodes are nodes which have no children. I don't know why the slide's in there. I'm skipping past it. The height of this is 2, because like all good computer scientists, we start counting at 0. So the depth of I'm explaining that to my 111 class again, and they're like, I don't like this at all. They really, really don't like that. Max, you go up to 5. You put 4i equals in range 5. So what elements do they count? 0, 1, 2, 3, 4. Where's 5? There are 5 elements in there. Not fans of it. There's a good reason. We get to it in core 1, core 2. We do explain it in core 2. Those of you who remembers from core 2, what? You remember something else, so clearly you have memory of core 2.
What were the middle ones called again?
You mean like 5, 2, and 6?
Yes.
Internal nodes.
Internal.
So height of 2, because that's the maximal height of the tree. Depth is 0, depth 1, depth 2. I need a clicker. That's unfortunate. It looks so pretty over there. It does. A data structure is not considered to be a tree if a child has more than one parent. It's also if a node points to anyone other than its parent, children, or siblings. The siblings is really a side case. We will look at, we're not going to look at many trees where you point at your siblings. It's really more of an implementation thing for how you point at your siblings. But there are ways to implement trees when you point to your siblings. What happens is your parent points to one child. So basically they point to the oldest child, and the oldest child's job is to keep track of all of their siblings. Oh, you think this is bad? Wait till parents start killing off their children. And then child node becoming the parent node. This becomes a dark, dark, dark class.
It's like threading processes.
Yeah, it's like threading process. You kill your child process. You wait until they're dead, and then you continue. Oh, this is so terrible. Yes. So anyways, so yeah, the other important thing to what the consequence of this, that this means you can't have cycles. So you can't have scenarios. So you can't have things like that, where one node points to another, points to another, points to another, points to something back. This is called a graph, and we'll talk about it later. You also can't have merging of branches. So one's a parent. There's no inbreeding here. Once 2 and 3 branch off, they can't reform. Any questions about this?
Why is it called a graph?
Why is that called a graph?
It doesn't look like a graph at all.
Maybe the graphs you know don't look like that.
I'm just confused why they keep using a bunch of words that are already used.
So So the reason why, so you're thinking, I assume when are you thinking about like wrapping paper where it's like that?
Yes.
So
Yeah, it's grid.
So the reason why, and we'll talk about this later, is this is actually it's actually a specific instance of that. If I were to take each of these crosshairs and replace them with a circle, and then make them connect the arrows between them, I've now turned into a graph. I'm not actually making this shit up. This is actually, graphing paper gets its term because the grid is a subcase of graphs. Because the man decided that graphing paper sells better than grid paper, not graphing paper, if we want to be specific about it. They decided graphing paper was a better marketing term. But yes, it's actually a graph.
So the same kind of general hierarchy kind of structure right here, is this the same way they do inheritance?
Yes, yes. And so inheritance can be mapped out with a tree structure.
Okay.
Tree structures occur all over the place in computer science. But yeah, now there are, this applies really more to subclassing rather than interface implementations, because with interface implementations, that's a tongue twister, you can have multiple, you can get multiple interfaces. With subclassing in good God-fearing languages like Java, you can only have one superclass. In monstrous subclassing languages, you can actually have 2 superclasses, and that's if you hate your life, you do that. If you decided, you know, I find computer science programming too easy, I would like to make this harder on myself without any good advantages, I'll have 2 parents. That's literally that's a conversation that everyone says when they have multiple inheritance.
What does this look like in a compiler? So like if you're displaying lists, you go 0, 1, 2, 3, 4, like when you print it off. But like what is a
How would I print this off?
how does a tree what is a tree?
That is an excellent question. No, it's not the next slide. Oh, damn it. It's like 7 slides away. So I'll talk about it now. I thought it was going to be the next slide, but it's actually several slides away. How we print this off, there's what?
Isn't it like you wrap around like line?
Yeah, so the idea here, and let's raise the roof or the screen. The idea is that you always want to start at the top node. So let's talk about how you navigate it. So you start navigating at the root node, and you traverse down the left connection, and then come down here. And once you've reached an end, you then loop back up like this. And so that's the standard, what's called depth first search, traversal of a tree, is you always go down the leftmost side. We'll talk a little bit more about depth first search in a bit. We used to always follow leftmost connections until there's no more, and then you loop back up to your parent, and then so if there was another node here, then you would have gone like that. Now, the way you would print this out, there's 3 different approaches for printing this off. I guess there's more, but there's 3 that human beings use. There's what's called pre-order, post-order, and in-order. Pre-order says you print off numbers, and so let's actually put a number here, 2.5. That as you see it, you print it off. So if I were to do an in-order traversal, what numbers would I print off? I'd say pre-order. Yeah, 5, 2, 1, 3, 2.5.
What?
In pre-order, you see it as the first time you hit it. 5, 2, 1, 3, 2.5.
Oh, I know.
Well, you didn't see this node that I covered up. 2.5, then 6, 12. Does this actually seem like a good idea?
No.
Yeah, there are times when this is useful, but generally when you're trying to see what is the list, not really what you want to do. So this is called pre-order. Let's do post-order. Post-order says the last time you say goodbye to a node, you print it off. So what would be the post-order for this? So when you leave a node for the last time.
2, 1, 3.
And it actually starts off with 1, because that's the first node you leave forever. Then 2.5, then 3, then 2, then 6, then 12, then 6, then 5. So it's called post-order. Now, in order, you can probably guess what this one's going to do. Just by the, if you were just to guess, which of these, have we done a sorted one yet?
No.
What do you think in order is going to be?
It's going to be a sorted
It's going to be a sorted one. Let's talk about what in order actually does. In order says that when you switch between the left branch and the right branch, so when you make that transition, that's when you print it off. Now, if it has no children, then you just print it off that way. If it has no left child, then then you just print it off when you see it the first time. So, in order traversal, 1, and then you come down here, we switch from the non-existent left to the non-existent right, that's when we print 1. We now come back to 2, we're switching from the left to the right, so we print 2. We go down to 3, again we switch from the non-existent to non-existent, 2.5, now we print 3 because we're switching from the existent to the non-existent. Now we go to 5, now 6 has no left child, so we're switching from a non-existent left to an existent 12. And so that prints attack, and then 12.
So it's just a coincidence there was a number order, because if that 1 had been a 5, 5 would have been the very first number in the list.
Right, and so this gets to an important point, which is that trees don't care about the particular elements that are in there. Trees can be implemented in any particular ways. What we're going to look at next class, is what's called a binary search tree. binary search trees always maintain the structure, that the left child is, everything in the left child is smaller than the parent, everything in the right child is smaller than the parent. And in that, the in-order traversal will always be sorted. But we'll talk about that next class. Cool. So that's it. I don't have office hours from 1 to 2 today because I'm doing the science day, big day thing. So if you want to come and talk about how awesome computer science is, I'll be in the Keck lab. And do anything else, you're more than welcome to do that. So, and remember, Cake says no classes this week. Cake says no classes this week. So, you can get it out.
He wants to JU test that lab.
Kramer gets the day off.
Yes,
He
yes,
only
yes.
has